Okay, so we learned about buffers on Tuesday, and we're going to continue that discussion. We are going to learn about what sorts of things make a buffer more or less effective. So one of the things is relative amounts of acid and base. So a buffer is most effective when the concentration of acid and conjugate base are equal. So what we're going to do is we're going to look at two 1 liter solutions of a generic buffer. This buffer has a pKa of 5, and we're going to calculate the percent change in pH when 0.01 moles of sodium hydroxide is added to each. So this is all kind of set up for us. So our first buffer solution has equal amounts of base and acid. In our second solution, we have a lot of acid and only a little bit of base. And so we're going to see how the pH changes when we add hydroxide. So we need a MICMA table, moles initial, change, moles after. So we're adding hydroxide, and we know that that is going to react with the acid in the buffer. So that's why those are the reactants here on our table. So we're adding 0.01 moles of hydroxide because that's what it told us we were doing in the previous screen. We are starting out with 0.1 moles of HA, our weak acid, because we have 1 liter of 0.1 molar, so we have 0.1 moles. We also have 0.1 moles of the conjugate base. So then we're going to look at, well, what's happening in the change? Well, the smallest amount of moles will get used up. So this one subtracts and we get to 0. We subtract that same amount from this one and we add it to the other side of the arrow. And now we get our moles after. And these are the numbers we can use to calculate the pH of this solution. Over here, we're doing the same process. We're starting with the same amount of hydroxide, but we've got 0.18 moles of acid and 0.02 moles of the conjugate base. And so the change is going to be the same, and we get our moles after. Because these are buffer solutions, we can use the Henderson-Hasselbalch equation instead of doing an equilibrium ice table thing. Do you have a question? No? Just look concerned. That's okay. So let's calculate the pH using that equation. So the pH is equal to the pKa plus the log of the base divided by the acid. So we have moles here instead of molarity, and it does say molarity here. The molarity of the base is going to be the moles of base divided by the volume, 1 liter. The concentration of the acid is the moles of acid divided by the volume, which is 1 liter. Because the volumes are the same for these, they have to be because they're in the same solution, the liters will always cancel out, and so we can do these with moles and take kind of a shortcut. If you don't like to shortcut, don't. You'll be fine. So pKa is 5.0 because they told us. And then,
Initial pH is 5.0?
Well, the initial pH is 5.0 and the pKa is 5.0. Yeah. So why is the pH the same as the pKa? Well, because when it starts, the amount of base is equal to the amount of acid. So when these are equal, this is 1, and the log of 1 is 0. So the pH equals the pKa when these are equal. So we added some hydroxide. They're not equal anymore. This is our base, 0.110. And our acid is 0.090. calculator's still in my pocket. So we've got 5 plus the log of 0.11 divided by 0.09. And we get 5.0872. So let's look at the other one. We're using the same equation, so I'm not going to write it over again. The pH for this one equals the pKa, not the initial pH, but the pKa, which is also 5, plus the log of the base, that's kind of a pitiful little 0 there, divided by the acid, so the 5 is the pKa. We were told that on the previous slide. 0.03 is, after we do the stoichiometry, how much base do we have? And 0.170, after the stoichiometry part, how much acid? So then we just type this into the calculator. And the pH for this one is 4.2467. This one started out at 4.05. Yeah.
I was gonna ask for the pKa for this one. Is it still 5 or is it 4.0?
That's a great question. The pKa for this one is still 5. The reason the initial pH is different is because we're not starting with equal amounts of acid and base. So if we plug these values into this equation, we will get 4.05. Great question. So this one was at 4.05. It went to essentially 2.5. This was at 5, went to 5.09. You know, it's like a little hard to compare, well, is that really different or not? So on the previous slide, they wanted us to calculate the percent change. So for the percent change, we're going to take the new value, and we're going to subtract the initial value and divide by the initial value and multiply by 100. And so this comes out to 1.7% change. And then we'll do the same thing for the other solution. Well, I don't know what I did there. Oh, I do know what I did there. I just messed up is what I did. Try that again. I messed up because I wrote it wrong. The initial pH was not 5. It was 4.04. 4.05. And I found a different way to screw it up that time. Third time's the charm, right? Okay, I think I got it. 4.9%. So this buffer, where the starting amounts of acid and conjugate base are equal, when we add something to it, the percent change in the pH is less than in the other solution where we have unequal amounts. And you could say, well, 1.7, 4.9, what's the big deal? Well, 4.9 is about almost 3 times as much as 1.7. And because the pH is a logarithmic scale, a difference of that much is a significant difference in concentration of hydronium ion. Any questions? Pardon me?
You said put it on sleep. How would we do this?
Put it on what?
Sleep.
Oh, that's a great question.
So,
So to be reasonably effective, the relative concentrations of acid and base shouldn't differ by more than a factor of 10. So it's best if they are equal, but they shouldn't differ by more than a factor of 10 to be considered a good buffer. Another way you can think about that is the ratio of base to acid should be between 0.1 and 10. So another thing that affects the effectiveness is the absolute concentration. So a buffer will be most effective when the concentrations of acid and conjugate base are high. You could have equal amounts but very low concentrations. That would not be as effective as equal amounts at higher concentrations. So we're going to look at that same generic buffer. We've got the tables all set up, but this time solution 1 has concentrations of acid and base 10 times higher than solution 2, and again we're going to calculate the pH change when we add 0.01 moles of sodium hydroxide. So here we have our tables for the stoichiometry part set up. Initial moles of acid and base, 0.5 of each, adding 0.01 moles of hydroxide. We do the stoichiometry, we end up with these numbers. Over here, we're also starting with equal amounts of HA and A minus, but they're 10 times lower, 0.05 instead. And then we're adding 0.01 hydroxide. So we do the stoichiometry, and now we can take these numbers and plug them into the Henderson-Hasselbalch equation, which is pH is pKa plus the log of the base over the acid. So pH here will be the pKa. This is the same buffer, so the pKa is still 5. And the base concentration divided by the acid concentration is going to be the same as the ratio of their moles because the volumes are the same and they would cancel out. In this example, because we have 1 liter, the concentrations and the moles and the molarity are the same anyway. 5 plus the log of 0.51 divided by 0.49. So here our new pH is 5.0174. So let's calculate that for the other solution. This also has a pKa of 5. And this has an initial of 5 also because it starts with equal amounts. But after we add hydroxide, it's not equal anymore. .1761. So the percent change will be our new pH minus the initial pH divided by the initial pH times 100. So this is 3.5% change. And over here, we can see already that this is going to be smaller. Zero 0.35%. So the percent change here was 10 times larger than the percent change over there. So the absolute concentration matters, the relative concentrations matter as well. Any questions?
Is it or one is better than the other, in the buffer?
This buffer is going to be better because when we add something to it, the pH changes less. This is a buffer, but it can't handle very much. So when we add the same amount, we get a bigger change in pH. So a better buffer will have less change in pH. Other questions? So we can calculate the outermost points of the effective pH range of a buffer. Because we said in order for a buffer to be considered effective, the base to acid ratio needs to be between 0.1 and 10. So here, base to acid equals 0.1. Just rearrange that. And for this one, base to acid equals 10. So we can use the Henderson-Hasselbalch equation to calculate the pH of a buffer like this and one like this. So the pH is equal to the pKa. We don't know what the pKa is, and that's okay, plus the log of the base over the acid. Well, for this one, the base over the acid is 0.1. So this gives us a result of pKa minus 1, because the log of 0.1 is negative 1. And down here, pH equals pKa plus the log of the base over the acid, which is 10. The log of 10 is 1. And so this will be pKa plus 1. So a buffer is most effective, or it is considered effective, within 1 pH unit of the pKa. The pKa is going to affect what the initial pH is. If I want a pH 5 buffer, I need to choose something with a pKa that is close to 5. And I could go, I can tweak the concentrations and make the pH a little higher or a little lower, but I don't want to go more than 1 pH unit from the pKa. Effective range for a buffering system, 1 pH unit on either side of pKa. So ideally, we would choose a buffer system that has a pKa that matches the pH that we want. It's not always possible. So then you adjust the pH by altering the ratio of base to acid. So let's do an example of that. This is a very practical question. Which acid would you combine with its sodium salt to make a solution buffered at pH 7.35? If you have 500 milliliters of a 0.1 molar solution of the acid, what mass of the corresponding sodium salt do you need to make the buffer? We have all the individual skills needed to solve this problem, but putting them together at this point is understandably challenging for students. Okay, so first let's think about what are they talking about when they say sodium salt? Well, we're going to have a weak acid, right? And when a weak acid ionizes, it forms hydrogen ions and the conjugate base. In order to have a buffer, we need the weak acid and its conjugate base. Can we add a solution of, say, acetate ions, all negatively charged? No, we can't, because nature hates it when we separate charges. Lightning is what happens when charges get separated. We don't want that happening. Not that we could make it happen, but. So we can't just add A minus. It has to have a friend with it. It has to have a counter ion. So if we choose Na, like sodium acetate, this is considered the sodium salt. Remember, chemists, when we say salt, we mean ionic compound. Any ionic compound is a salt. Salt, in everyday language, means table salt, which is sodium chloride. That is one of many salts. So this is what they mean by sodium salt. Because when you dissolve that ionic compound in water, it dissociates completely and forms sodium ions and that weak base that we want. Do we care about the sodium ions in there? No, they're not going to do anything. They're just going to float around and keep the solution neutral. They're just going to watch and not participate. So we could use sodium, we could use potassium, we could use anything almost. Sodium is easy and common. Okay, so that's what that means. We want a buffer with a pH of 7.35. Which of these acids would be the best one to use? We're going to look at the pKa, and we want the one that's closest to 7.35. This is not a trick question. HClO, right? This guy at the bottom. We want to use that one because its pKa is closest to the pH that we need. To adjust the pH, we need to adjust the ratio of base to acid. Ideally, those would be equal, but at least they need to be within a factor of 10. So it's best if we start with whatever is closest. Okay? So that's the one we're going to choose. And we want a pH of 7.35. So this tells us we have 500 milliliters of a 0.1 molar solution of the acid, this acid. We need to know what base concentration do I need for the pH to be 7.35. Because I need to know what base concentration I'm looking for before I can calculate the mass of salt that I should add to make it that. And we can use the Henderson-Hasselbalch equation to help us figure this out. So it's going to be used a little bit differently. We're not solving for pH here. We know what pH we want. We want pH 7.35. 7.35 is going to equal the pKa, this guy down here, plus the log of the base concentration over the acid concentration. Well, the base concentration is what we're trying to figure out. Divided by the acid concentration. What's the acid concentration? It's 0.10. They told us that. okay? So we've been using this equation, but now we're going to use it in a different way. So we need to find the base concentration. If you're good with algebra, you can rearrange this on your your calculator pretty easily and figure it out. If you don't like algebra and it doesn't like you, use the solver on your calculator. It's not just good for quadratic equations. You can use it for anything. It's amazing. So you just plug this equation into your solver just the way it looks, except you can't type in base, but put an X there, okay? So some of you do it with the solver, and I'm going to do it with algebra because I happen to like algebra. And I get that we need a base concentration of 0.06457. What does the solver tell you? Same thing. This is not an approximation that I'm doing here, so we should get the same number. I didn't write down all the digits the calculator gave me, but I just wrote down 4 sig figs. We should get the same number. Okay, so now we know that we need 0.04606457. Learn how to read. Molar, and what compound is that? It's the sodium salt of this. So that would be NaClO. So that's the molarity. And what volume do we need? We need 500 milliliters. So I want 500 milliliters of 0.06 molar NaClO. So this is going to be a dimensional analysis problem. We are starting with milliliters of buffer, and we want to end up with grams of NaClO. And we need to figure out how can we get there. It's not necessarily obvious. Sometimes it's obvious. Here, it's probably not obvious, so then we need to stop and think about it. Sometimes we can just start at the beginning and go to the end. Other times we may need to start at the end and kind of work backwards until we see, and we'll meet up somewhere in the middle. So here's grams, and I've got molarity. I'm going to need to use that in there somewhere, right? That's moles per liter. So I'm going to need moles in there, right? If I had moles, could I convert that to grams? Yeah, I could do that. So before I get to grams, what I need is moles of that salt, right? This moles per liter is a conversion factor that relates moles and liters. So the thing that comes before this is liters. And can we go from milliliters to liters? Yes, we can. So this is the path. You don't absolutely have to write it down. But if you struggle with word problems, I highly recommend that you write it down. Or even if you're just easily distracted. Because you get in the middle of this and then you're like, wait, what was I doing? Well, here we have it written down. This is exactly what we're doing. So this path gives me the units in my equation. I'm starting with milliliters. Every arrow is going to represent a fraction. So I've got 3 arrows. I'm going to have 3 fractions here. I'm going from milliliters to liters, just like down here. And the next fraction, I'm going from liters to moles of NaClO. And the next one, moles of NaClO to grams of NaClO. If you had me for 1A, you saw me do this a gazillion times. If you didn't, this might be new to you, or a new way of thinking about dimensional analysis. So, any questions about what we've done so far? Everybody okay with that? So those are my units. Now I need to get rid of milliliters, so that goes in the denominator here, and those cancel out. And I need to get rid of liters, so I put that one down here. Those cancel out. I need to get rid of moles, so I'm going to put moles down here, and those units cancel out. This is analyzing the dimensions, dimensional analysis, using the units to guide me in what kind of math to do. You put all of the units in first, and then the units show you where to put the numbers. It's so much less thinking. Well, let's look at the first one. I need to know the relationship between liters and milliliters. I need to know what that prefix milli stands for. So it's 10 to the minus 3. So milli stands for times 10 to the minus 3. You can look it up if you've forgotten. We're not going to think about, do I multiply by 1,000 or divide by 1,000? We're just going to use the prefix. So I have the prefix down here. So 1 milli is the same as 1 times 10 to the minus 3. Using this method, the prefix and the number are always on the opposite side. They're never together. This is like a nickname for 1 times 10 to the minus 3. Call it milli for short. Okay, moles to liters. Well, that's the molarity. That's what we calculated up here. And it's always a good idea to write out those units instead of just the capital M. This is moles per liter. Because sometimes capital M morphs into something else in your brain, and I see all kinds of things like molarity canceling with meters or moles or all kinds of strange things. The capital M is moles per liter. We just use that because it's a lot shorter. We're writing these concentrations on all kinds of bottles, and it uses up a lot of label tape, right? Nothing else. So moles per liter. The number is with moles. So I'm going to put the number with moles. I did not leave enough room. It's okay. I'll squeeze it in. Per how many liters? Well, per each liter, right? Per 1. If it bothers you to not have a number there, write the 1 down. And then grams and moles of NaClO. How do we find that? Molar mass, right? Periodic table. So sodium is 22.99, plus chlorine is 35.45, plus oxygen is 16.00, 74.44 grams per mole. Now, how do we solve this on our calculator? We are not going to combine all the numerators and write it down, and combine all the denominators and write it down, and then divide. We're not going to do that. We're just going to start at the left and go straight across and do it all in one shot. I'm going to take 500 and I multiply by the numerator, I divide by the denominator. I multiply by the numerator, divide. Multiply, divide. If you do each fraction completely as you go along, you won't forget anybody. Now, do you have to divide by 1 on your calculator? No, you can skip that. But if it bothers you, you can do it also. And when you do scientific notation, please use the scientific notation button. It's EE or EXP. So 500 times 1, EE negative 3, times 0.06457, times 74.44. And calculator says 2.4033 grams. How many sig figs? Well, in our pH, we have 2 sig figs, and in this concentration, we have 2. So it's reasonable to say, let's use 2. So I would need to add 2.4 grams of sodium hypochlorite to this acid solution to get a buffer with pH 7.35. You know, if you're ever in a situation where you need to make something like this, and you know, if you don't write down your calculations, and then you won't use 2.4 grams, they're going to go like, well, how do you know that? Show me. I don't believe you. It's kind of complicated. We need to be able to show our work when necessary. So we use HClO, 2.4 grams of the sodium salt. So we talked about buffer effectiveness. Buffer capacity is the amount of acid or base that you can add without causing a large change in pH. And so buffer capacity is kind of a qualitative thing, not a quantitative, because how do you define large, right? But the buffer capacity, how much stuff it can handle, will increase with increasing absolute concentrations, and it will increase as the relative concentrations become more similar. So the same 2 things that made a buffer more effective also gives it a higher capacity. If you have a buffer that needs to neutralize primarily acid or base, you know what kind of stuff is going to come into this, and maybe it's all going to be acid. It's not going to have to neutralize any base. Well, then you overcompensate, you overweight one of the categories. So if I'm going to be adding a lot of acid, then I want my buffer to have more of the conjugate base, because that's what's going to do all the work. If I'm going to be adding base, I want more of the weak acid. So here we have an illustration of a concentrated buffer and a dilute buffer. So here we've got, just a few particles that are able to neutralize something. In the concentrated buffer, we have more. And so this will have a larger capacity. Any questions? Yeah. So if our weak acid and conjugate base are higher in concentration, we'll be able to take care of more added stuff. So here we've got more acid and base, so if I put acid in here, this can take care of more acid than that one can, because this one only has 2 of the conjugate bases, whereas this one has, 5? 6? It's got 6 of them.
So if we put more acid, it's gonna be better buffer?
So this will be able to handle more added acid. Okay, so I could add 6 molecules of acid to this, and the base would be able to neutralize it. If I add 6 here, only 2 of them get neutralized, and I have 4 left that just are going to sit there and make it acidic.
So it is not good buffer.
This is not as good. So we want higher concentrations, and we want the concentrations to be equal. Those are the best for a buffer. Any other questions? So we have a 1 liter buffer that is 0.1 molar in HF and 0.05 molar in NaF. Right? And this is the sodium salt of the conjugate base of this weak acid. Right? We replace the hydrogen with sodium, that's the conjugate base. So this is asking which action will destroy this buffer. So we have 3 different choices here, plus none of the above. Don't you hate that? So let's analyze these choices and see, well, what's different about them and what's the same? Well, what's the same is they're the same amount of stuff, right? It's the compound that's being added that's different. What kind of a substance is HCl? It's an acid. What kind of an acid? A strong acid. And what kind of a compound is NaOH? A strong base. What kind of a compound is sodium fluoride? It's a salt, right? Is it going to be pH neutral or acidic or basic? It's going to be basic because this is the conjugate base of a weak acid. So the F minus is going to act as a weak base. Okay. If I add HCl to this buffer, which of these is going to need to neutralize the HCl? The weak acid or the conjugate base? Which one will neutralize HCl? The conjugate base will neutralize added acid, right? So adding acid, it's going to need this guy. If I'm adding base, strong base, what's going to neutralize it? The acid, right? Okay, so equal amounts here, but the amounts of weak acid and conjugate base are not the same. We have less of the weak base. So what's going to be worse for this buffer, acid or base? Acid. So A is going to be our answer. That's going to destroy the buffer. Because you can think about it this way too. A 1 liter buffer that's 0.05 molar, that's 0.05 moles of F minus. And we're adding 0.05 moles of strong acid. That's going to use up all the conjugate base. And it won't be a buffer anymore then. What if we add more F minus to this? Is that going to destroy the buffer? No, it won't. It'll make it better, actually, because we're kind of short on this. This would be better if it was 0.1. So if we add another 0.05 moles of NaF, then we would get equal concentrations, and the buffer would actually be better. Any questions?